So this lecture is going to be the first lecture on Fourier transforms for ECE 343. Last time we completed our discussion of the Fourier series. The Fourier series is a method by which we look at signals that are both continuous time and periodic. The Fourier transform is a technique that allows us to take a look at continuous time signals that are aperiodic. In order for us to understand the Fourier transform, to derive the Fourier transform result, we're going to use a method very similar to what's done in the book in Chapter 7. And we're going to take a look at a aperiodic signal, and I've drawn a picture of a typical one here. So I've drawn a signal in red that I've called x of t. We can see that this particular one is finite duration, so it has a finite interval for which it is non-zero. It makes it easier to visualize this way, but it's not a requirement. This is not something that we have to have true in order for the discussion that we're doing here to hold. The next thing I'm going to do is I'm going to go ahead and periodically replicate this aperiodic signal x of t. Basically, what does that mean? I'm going to just make copies of x of t, every integer multiple of some base interval t naught away from the original. We can see that in our second picture here. There's the original copy that's still in red, but then we start seeing other copies grow away from that center copy. There's one at t naught, there's one at minus t naught, and we'd see them at every integer multiple of t naught. So 2t naught, 3t naught, all the way out to infinity, minus t naught, minus 2t naught, all the way out to minus infinity. So x tilde sub t naught, x tilde just tells us it's a periodic replication. The sub t naught tells us the period of that replication, so that cap t naught is just the period, and it is still a function of time. So x tilde sub t naught of t is a t naught periodic extension or replication of our original signal x of t. If I wanted to write an equation to do this, that isn't all that difficult either. I could say that periodic replication, x tilde sub t naught, is just what? It's a summation, and we can sum over a bunch of copies, k equals minus infinity to infinity, and we're just making it up out of our original signal x, and it's going to be that signal shifted by integer multiples of the period, t naught, so k times t naught. If I took that notation and I expanded it out term by term, I'd find that center piece, right, would correspond to k equaling 0. Though the piece right to the immediate right there would be k equaling 1. The one to the immediately left of the origin would be k equaling minus 1, and so forth, and it goes out to infinity. The overall period then of this signal, it is a periodic signal, is t naught. A couple things to note on this. One of the things that we can note here is that the original signal x of t, which I've shown in red, is equal to that periodic signal, x tilde sub t naught of t, in the limit as the period goes out to infinity. What is that basically saying? Well, if I take a look at these periodic replications, so there's a replicate, and there's a replicate, right? And what are we doing? We are forcing those guys way the heck out. We're pushing them out as t naught goes to infinity, so they go flying off to the right. And as they go farther and farther and farther away from the original, right, the original is the only thing that is left. And so as that period t naught goes out to infinity, we would not see a difference between those two plots. They would look equal. These guys are equal if we let t naught go to infinity, something along those lines. So why do we think about that? Part of the reason is this. X tilde sub t naught being a periodic signal is something that we can analyze using tools that we already know, the Fourier series. And if I can just look at it using those tools that I know, but then let that parameter t naught go off to infinity, I can start understanding what the tools will look like to look at aperiodic signals. So we will take a look at this signal, x tilde sub t naught. We can analyze x tilde of t naught with a Fourier series, right? And then we're going to look at what happens as the period goes off to infinity. That should give us an idea of what this Fourier transform is all about. A little reminder about the Fourier series. This is all stuff from our previous lectures. This equation, which I've labeled 1 in green, is the Fourier series synthesis equation. I can create this periodic waveform, x tilde sub t naught of t, and I can do so as a linear combination of harmonically related sinusoids or complex exponential functions. So I have a summation of some coefficients, cap x tilde of k, right, times these basis functions, e to the jk omega naught t. How do I get the size or those Fourier series coefficients, the cap x sub k? Well, we can get those guys using our orthogonality principle or the Fourier series analysis equation. And we know that is 1 over the period, integrate over the period, then the signal times the conjugate of our basis functions, e to the minus jk omega naught t, and integrate out time. Okay, so some things that we might do with that equation, the Fourier Series analysis equation. I'm going to take a quick look at this. This is integrating over a period my periodic signal, right? Let's go ahead and go back to the graph and look at how we might do that. I might come in here going from minus t naught by 2 and go to t naught by 2, right? That creates an interval, right? That is t naught in width, and my integral is of x tilde sub t naught over that interval t naught, which I've taken here as being minus t naught over 2 to t naught over 2. And what I can notice there is that over that interval, the only thing I see is that red waveform. That is exactly the same as x of t. And because x of t is 0 everywhere outside, right? We could take that integral going from minus t naught over 2 to t naught over 2, right? And we could replace it with an integral of x of t, not the periodic signal, but the aperiodic signal. So we could do an integral of x of t going from all the way at minus infinity all the way to plus infinity. And so it's just a little game we're going to play. It's a way of incorporating or putting x of t into this expression for the Fourier series coefficients. So what have I shown there in the graphs? Integrating x tilde sub t naught of t over that interval t naught is the exact same as integrating my original aperiodic signal x of t over the interval minus infinity to infinity. What does that mean? That means I can take this Fourier series, right, analysis equation, and I can rewrite it. I can rewrite that as x tilde of k, right, as being 1 over t naught. That doesn't change. All I'm changing now is the integral. The integral is now going minus infinity to infinity, and it's not of x tilde, it's going to be of xt. Everything else is the same. We still have the e to the minus jk omega naught. It's still dt, and we still have that parameter or that factor, that constant out front, 1 over t naught. Okay, so I'm going to next define a continuous function of omega, and I'm going to call it x of omega. Part of this is because I know where I'm going. I'm going to define a function of frequency omega called x of omega that's going to be an integral minus infinity to infinity of x of t e to the minus j omega t dt. Okay? Now, if I compare these two equations, so if I do a comparison between what that Fourier series equation was and this defined continuous function of frequency, right? What do we see? We see that they both involve an integral from minus infinity to infinity. They both involve little x of t, which I've shown in red. They both involve an exponential. One is the exponential e to the j k omega naught t. The other one is e to the j omega t. So as long as I was thinking of omega being like k omega naught, those are the same. And then the other one has an extra scale factor out front, 1 over t naught. Comparing these guys, what do I see? I see that these Fourier series coefficients, the x tilde of k, right, look like scaled and sampled versions of that underlying continuous distribution x of omega. So in other words, if I came back up here to my x of omega, right, and I went ahead and I took a look at this at omega equaling k omega naught, and then I took that whole thing, right? Whoops, and let's go ahead and make it the whole thing. If I took that whole thing and I multiplied by 1 over t naught, what I would find is that I'd get x tilde of k, right? And it just would be that continuous time underlying distribution, sampled at different values, k omega naught, and then scaled in amplitude by 1 over the period, 1 over t naught. So what does this do for us? This relates the Fourier series coefficients. These are the coefficients that came out of my periodic replication of that aperiodic signal to make that x tilde. The Fourier series coefficients for that guy look like scaled by 1 over t naught, sampled some underlying continuous spectrum, which we called x of omega naught. As t naught increases, the sampling density increases as well. Let me try to show this with an example. So what I've shown here on the left, right? What I've shown on the left here is a particular underlying spectrum, call it x of omega. I've drawn that with a black line. It looks like this kind of exponentially decaying envelope. And then I'm going to go ahead and sample that, right, at some integer multiples of some base frequency omega naught. So I'm going to take k times omega naught, and I'm going to get a bunch then of sample values of that, and then I'm going to multiply them all by 1 over that t naught. So if I look at the blue line at the origin, that is a k equaling 0 term. The next blue line is k equaling 1, which is a frequency is going to be omega naught, right? The next one is k equaling 2. That's going to be 2 omega naught because we're just taking omega at k times omega naught. The next one is at 3 omega naught and 4 omega naught and so forth, right? So I'm just taking the underlying distribution, that's a solid black line, I'm sampling it at integer multiples of some base frequency, omega naught. That gives me a spacing in frequency. The horizontal axis here is frequency, omega, right? Horizontal axis, and these guys is frequency. And so I just get a bunch of samples of that underlying distribution, and the overall height depends something on that overall period, 1 over t naught. Now, if I double the t naught, what does that do? If I double the t naught, right, that makes omega naught half as big, right? Why do I say that? Because I know that omega naught equals 2 pi by t naught. So if I double t naught, because omega naught is reciprocally related to t naught, we know that the omega naught for that double size period is going to be half as big. So it's going to be a tighter sampling density. That goes back to this original statement here. As the period increases, the sampling density also increases. So if you take a look over here, I had some interval width here, whatever that was in frequency, however many rads per second that might have been, going from the DC to that first sample. When I come over here and I look at it on this other graph, I'm going to see twice as many samples in that same interval because I doubled the period, and that means I doubled the sampling distance or the sampling density. The peak height, because the peak height is reciprocally related to period, and I doubled the period, that means the peak height goes out half as big as it was before. So whereas before, right, I had this peak height coming out there that was some amount, whatever it is, that peak height over here is going to be smaller. It's going to be half that value because of that 1 over t naught relationship. Remember that x tilde of k looks like a 1 over t naught of some underlying continuous distribution, that's the solid black line, right, sampled at integer multiples of whatever the base fundamental frequency is. And as the period gets bigger, the base frequency gets smaller. That means that they're going to be more densely packed together. So what do I get? I get twice as many lines, right, that go twice that go half as high. Now, if I doubled the period again, what would I get? I'd get twice as many samples from the one I see on the right. And I could keep doing that and doing that and doing that. And what you would see is you'd keep getting more and more samples filled in until, in the limit as you go out to infinity, it smears into a just continuous line. In the limit, as t naught goes off to infinity, right? As t naught goes off to infinity, this set of line spectra become a continuous distribution. But also, because that 1 over t naught period being, or that 1 over t naught factor being out front, the amplitude becomes infinitesimally small. So we know that that sampling density keeps getting tighter and tighter and tighter, and we know the amplitude gets smaller and smaller and smaller. That is, this whole thing becomes a density function. You might have seen density functions before. You might have seen them in a physics class or maybe in a mechanical engineering in their introductory classes. If you haven't seen a density, you could have seen it in a random processes class. We talk about probability densities in there. If you haven't seen a density before, I think we can still get a pretty quick idea. So let's do a little aside and talk about density. By the way, this density that we were talking about in the limit, as we let cap t naught go off to infinity, that means the number of samples gets really, really big, infinite, basically. And instead of just a bunch of spectral lines, we get a continuous distribution, right? Because there is no period, and the height becomes infinitesimally small. We call that a spectral density. It's a distribution of signal content, signal energy over frequencies, and that over frequencies, a term for that is the spectrum. So let's do a little aside on this and think about maybe one way of thinking about density functions. I've shown here on the left a board, and that board's sitting on a little pivot point on a fulcrum. And I've taken a shovel and I've thrown a shovelful of sand onto that board. If you were around Fargo during the major floods that we've had in the past, we had a lot of sandbagging operations, and you certainly could have had some examples of doing this, where you took a shovelful of sand and you put it in a bag or on a board, something along those lines. So I've got this distribution of sand across the board, okay? This is, in a way, we can visualize this as being a mass density function, okay? We know that this sand has mass. We know that when I take a shovel full of sand and I throw it on something, if I have to pick that up, I have to pick up whatever that amount of sand I threw on that board is. And that's heavy, right? So there is some mass in there. However, if I do something like this, if I sit there and I say, how much mass is there above, right, a particular point? So I'm showing an arrow here pointing a little bit off center. And if I say how much sand is above that single point, well, we could look right above that guy, and as we go across that, what we'd find is, because a line is infinitesimally wide, right? It is a very, very narrow piece, right? A line has no width. In fact, we could say with a great amount of certainty that there is no sand above it. That line, as it goes forward, perfectly splits between every single atom of sand that there could be in there, because the line itself has no width. Okay, so this is sort of a little bit strange, right? If I look over any particular point, there is no sand. However, if I start thinking about how much sand is there on an interval, I know there is sand. So how do I get that? I can do it by taking a density function. It tells us how much sand per unit length is there. And I can get the amount of sand by basically integrating that density function. So here I might have picked an interval here. I've shown it with these two lines, red. And then I would do what? I would integrate my density function. This density function tells me what? Because it's taller in the middle, that means that there was more sand or more sand density towards the center of the board, and that the sand density towards the edges of the board got less. So if I integrated that up, okay, that amount of area would be able to tell me the total amount of mass, something like kilograms of sand. I do that by integrating a density function. Okay, so we can go to a similar idea to a spectral density function. A spectral density tells us what is the frequency content of a signal as a function of frequency. What's the spectral density, right? What's the density function? What's the amount of frequency content we expect in the vicinity of a particular frequency? Now, if I look at a particular frequency of interest, so I looked at one here that's red, and I said, how much, right? How much frequency is there? Because this is a density function, right? That particular frequency, whatever I chose it to be, I could call that guy omega naught. There is absolutely no omega naught content. If I was gonna just take that signal and I could have a perfect band pass filter that only allowed omega naught through, right? We'd find out that basically nothing would come out, right? Because there is no area over a single point. So for density functions in general, right, it is not possible to sit there and talk about content at a particular frequency. What makes sense is that you start talking about content over intervals of frequency. So that density function, you will integrate it, right? And once we integrate it, that integral amount will tell you the corresponding amount of signal energy that corresponds to frequencies in that range of whatever that interval is. Here it might go from some minus omega naught to omega naught, or minus 10 to 3, or whatever the interval it is. Density functions tell you the distribution of energy. For sand, it was the distribution of mass as a function of length on that board. For our case of a spectral density, this is distribution of frequency content of our signal, or content of our signal, or energy of our signal as a function of frequency. We aren't going to generally be interested in whether this signal has 2 hertz content or 3 hertz content. Instead, we're interested in how much content does it have between the frequencies of 2 and 3. So we're going to look mostly at intervals rather than just individual points. Okay, so if I take my equation 2, and if you go back up in here, I had just called that equation 2, right? I'd called this equation 2, this relationship between my Fourier series coefficients x tilde of k and the underlying continuous distribution x of omega. If I take that equation 2 and I plug it into equation 1, which was my original Fourier series synthesis equation, what I get is the following. I can synthesize my waveform x tilde sub t naught of t, right, as a sum, right? We knew it was a sum, and it's a sum of weighted basis functions. Our basis functions are those harmonically related exponentials. It's just now, instead of the x tildes, we're putting in those sampled and scaled values, right? Those sampled and scaled versions of that underlying continuous density function, x of omega. We know as t goes off to infinity, this omega naught, which is 2 pi by t naught, goes to 0. So there essentially is no fundamental frequency. That's no surprise because it's not a periodic signal anymore. If the period goes out to infinity, it's not periodic. Let's utilize a little bit more familiar notation, something you should have seen back in calculus. Let's call delta omega 2 pi by t naught just as being this omega naught. So I can rewrite that equation we just had, right? So if I take a look at this equation we just had, and I'm going to rewrite it in a slightly different format. I'm going to let that x tilde sub t naught of t, I'm going to construct it. That's a summation minus infinity to infinity of xk delta omega. We're going to have a delta omega over 2 pi. That's just substituting in for what was t naught. And then I'm going to have an e to the jk delta omega t. This is still the basic Fourier series, the Fourier big story that x tilde k is comprised of frequencies, and that should not have been a k. This is x tilde of t, right? That x tilde of t is comprised of frequencies k delta omega. As t goes off to infinity, right, delta omega goes to 0, and we know that x tilde goes to x, right? As the period goes off to infinity, our periodic replication converges to our original aperiodic signal. That tells us x of t is equal to the limit as t naught goes to infinity of our x tilde. But what was x tilde? It was that expression above. So we just look at the limit as t goes off to infinity, and I'm going to clean that up a little bit. I'm going to pull out the 1 by 2 pi factor. I've got a sum k equaling minus infinity to infinity, and I've got x of k delta omega, e to the j k delta omega t, and then a delta omega. You've done this kind of limit in calculus. And as t goes off to infinity, we could have also done this in the same sort of way. This is a limit as delta omega, right, goes to 0. It's the same sort of thing. This is one of the things that you should have seen in calculus, probably the Calc 2 class, in how you derived or how you motivated this idea of integration. So in the limit as t naught goes to infinity, or as delta omega goes to 0, that sum becomes an integral, and the k delta omega becomes omega, right? And we can rewrite that expression now. And we write that expression as being our signal x of t, and that's the aperiodic one, right? And we were able to get that x of t back in because we related the underlying spectrum with those Fourier series coefficients, the x tildes. So our aperiodic signal x of t can be gotten as 1 over 2 pi, an integral minus infinity to infinity of those Fourier series coefficients, or the Fourier transform coefficients, that underlying density function, that thing I said underlined all the samples that we looked at before, x of omega times e to the j omega t. This is actually something that should look pretty familiar. What does it tell us? It tells us that our aperiodic time domain signal, right, is just equal to a sum of scaled, right, complex exponentials. The only difference between this expression and what Fourier series synthesis equation gave us is that the frequencies omega are not required to be harmonically related. And it makes sense that we don't need harmonically related frequencies because there is no underlying period. It is not a periodic waveform, so we don't need every single frequency there to share the same period. They can be chosen from a continuum of frequencies. So we truly do get something that can have frequency going from 0 out to infinity. This is the Fourier Transform synthesis equation. How did we get it? We got it by taking our signal, x of t, periodically replicating it. That gave us x tilde. I let that period go out to infinity, so I did t naught going out to infinity, and then I took a look at the resulting distribution. Did a little bit of extra math in there, but in that end case, letting that period go out to infinity, we were able to build out this Fourier Transform synthesis equation. That underlying aperiodic signal is just a linear combination of complex exponentials. It's now a continuous sum rather than a discrete sum, right? So we're integrating rather than doing a sum over a countable number of points. If we go back to what I'd given as, because I knew where I was going, what the spectrum was, that's just x of omega. Let's do that in a different one. Let's do that as a highlighter. X of omega is just an integral of xt e to the minus j omega t dt. Compare these two equations with what we had for Fourier series, and they're going to look very, very similar. We'd already mentioned that the Fourier transform synthesis is like the Fourier series synthesis, except for what? We get an integral instead of a sum, and there's this extra, 2 pi factor out front. That has to do with us using radian frequencies. When we take a look at the Fourier transform analysis equation, that looks a lot like the Fourier series analysis equation. Instead of integrating over a period, well, because there's no period to integrate over, we just integrate over the whole signal, right, times the conjugate of our basis functions, e to the minus j omega t. Again, because there's no period, we don't go over k omega naught, we just go over some omega. So these guys look very, very similar. If you want to think about one other element or one other structural kind of nicety about Fourier transforms instead of Fourier series, it's this stuff that's noted over on the left side of the page here. It says, note the near perfect symmetry between the analysis and synthesis equations. Let me see if I can highlight this as well. We are going to be taking in the Fourier transform synthesis equation, right? We take something in the frequency domain, that's x of omega, right? And we weight it by an exponential, so x of omega times e to the j omega t, so it's a product of two signals, integrated, right? And then we have a scale factor, and we get out the signal in the other domain. So this took a frequency domain signal, cap x of omega, and it returned to us a time domain signal, x of t. And it did so by taking the frequency domain signal times an exponential integrated. If you take a look at the Fourier transform analysis equation, it takes its corresponding signal, this is a time domain signal, x of t, it multiplies it by an exponential e to the minus j omega t, and integrates it, no constant now, no 1 over 2 pi, and that gets me the other domain, cap x of omega. In both cases, right, we are getting the desired signal, whether it's x of t or x of omega, through an integration of the other domain, x of omega or x of t, times an exponential. The only differences between these two equations are the following. One has that scale factor, 1 over 2 pi, and there is a difference in sign, right, in that one exponential. Those are the only differences. Structurally, they look essentially the same. A scale factor is not a big deal. That just makes one thing a little bigger or a little smaller than the other. And in fact, that scale factor would disappear if we chose to do this in terms of Hertzian frequency instead of radian frequencies. If I did, we know that what? We know omega equals 2 pi f, right? And that means d omega equals 2 pi df. If I plug that in, that 2 pi that would come in through the differential element when I get to df would cancel with the 2 pi out front. So we could even get rid of that difference of 1 over 2 pi if we just went with a Hertzian notation. So the only really substantive difference between these two equations is that there's a minus sign in one of the exponentials that's not in the other. This is the basis of one of those properties that we had mentioned before that we said we were going to spend a little more time on. We'll do that next lecture when we talk properties. This idea of duality. Whatever result you get going in one direction tends to be the same kind of result you would go in the other direction. If I had some signal x of omega and it had a particular form like a rectangle function, and I found out what the corresponding time domain signal was, it would turn out to be a sinc. We'll see that later as we do some examples. Well, then if I had a rect function in time, guess what? Its spectrum is going to be sinc-like, because what goes in one direction tends to go in the other direction, and it's because of this near perfect symmetry, the fact that the analysis and synthesis equations look virtually identical in the Fourier transform case. Instead of one just being an integral and the other being a sum, like we had with the Fourier series, for the Fourier transform, it's all integration, and actually that usually makes most people a little bit happy, because the integration integration is a little bit more familiar when we're at this level, a little easier to carry out. We can write this in a little more compact way. I can say that my Fourier transform x of omega, that's the spectrum, is a script f, right? The Fourier transform of little x of t. So that script f would be read the Fourier transform of. So I could say my spectrum x of omega is the Fourier transform of x of t. In the other direction, I could say that my time domain signal x of t, right, is the inverse Fourier transform of x of omega, right? Something along those lines. So just a little bit shorter hand notation. X of omega is referred to as the spectrum of our signal x of t. It is a frequency domain representation of the time domain signal x of t. Since x of omega is generally a complex function of omega, we usually look at the magnitude of x of omega and the angle of x of omega separately. The magnitude of x of omega is called the magnitude spectra, or magnitude spectrum. I probably should have written that as spectrum. So let's go ahead and do that. Get that in there, magnitude spectrum. So magnitude x of omega is the magnitude spectrum. Angle of x omega is the phase spectrum, just exactly like we had with the Fourier series. The Fourier series coefficients were cap x of k, and if we looked at the magnitude, that was called the magnitude spectrum, and the angle of x of k was the phase spectrum. So we can do the same game in here. It's based on a polar decomposition of that function x of omega, that spectral density. So we have magnitude spectra and we have phase spectra. And usually if we were wanting to plot these frequency information out, we would do it as a pair of plots, right? The magnitude spectrum and the phase spectrum as well. Okay, so that's how the book derives the Fourier transform. I'm just going to say as a fun aside, I'm not going to go through every last detail on this, but since we had spent so much time talking about the orthogonality principle before, let's take a look at how the orthogonality principle could have handled this guy. So as a fun aside, we're going to derive the Fourier transform using orthogonality. How do we start? We say that our original signal, x of t, that's our signal, is going to be represented as a linear combination of basis functions. So x of t wants to be a linear combination of basis functions. Because there's no underlying period, there's no limitations on frequencies, so this linear combination is going to be a linear combination kind of in the limit. So instead of a discrete sum, it's going to be a continuous sum, an integral. So I'm going to have an integral of some coefficients times my basis functions, e to the j omega t. That is our Fourier series synthesis equation. It just says I'm going to approximate my signal as a linear combination of basis functions. It turns out, just like for the Fourier series, those basis functions are orthonormal basis functions. That means if you take two different frequencies, their inner product is 0. If you take the same frequency and look at its norm squared, it's going to have a norm squared or a size equaling to 1. It's the good kind of basis functions. If I'm interested in finding, right, the overall best coefficients, x of omega, if you want, to make this approximation turn out well, to minimize the norm squared error, we know that those best coefficients satisfy the orthogonality principle. To do that, we need to know what the inner product is. So I'm just going to define an inner product that's consistent with our idea of energy. The inner product between a and b is going to be an integral of a times the conjugate of b. So if I did the inner product of a with a, I would get the integral of a times a conjugate. That would be the integral of the magnitude of a squared. That is defined as the energy of the signal. So much like the Fourier series was based on an inner product that was connected to power, here we're picking an inner product that is connected to the idea of energy. Okay, so if I know that I have orthonormal bases, right, and I know what my overall inner product is, I can get that best solution, cap x of omega, as just being the inner product of x, the signal of interest, right, with the basis functions, the building blocks that we're doing. So the inner product between x and phi. And what was the inner product? It was an integral of the first thing times the conjugate of the second. Plug that in, and what do I get? I get exactly the same result that we had through all that other math. It says that cap x of omega is an integral minus infinity to infinity, x of t e to the minus j omega t dt. That is a Fourier transform analysis equation that we derived in a different way by making a periodic replication and looking at what happens when the period goes out to infinity. I actually think that the derivation by orthogonality is much more elegant, but it does have a little more math background in order to do it. You could take your pick on these two as to which one you like. They both give us the same result. Like the Fourier series, we know that at least if the signal itself is square integrable, that means it has finite energy, then the Fourier transform converges in the mean. We talked about this when we discussed convergence of the Fourier series. Fourier series or Fourier transform, both of them, as long as you have a square integrable or a square summable function, they converge in the mean. What does that mean? That means that if you look at the Fourier transform approximation to a signal, right, if we use this Fourier transforms synthesis equation, that's this guy right here. If we use that synthesis equation based on the spectrum of a signal to return or approximate our original signal, those approximations are going to be the same in that the difference of them, right, will have zero energy, right? So the difference between those two signals will have zero energy. It does not guarantee that they converge or that the Fourier transform converges pointwise. In order to get something close to pointwise convergence, you need to satisfy these Dirichlet conditions. And we had talked about those, at least the corresponding Dirichlet conditions for a periodic signal. We'll look at the analogous Dirichlet conditions for this aperiodic continuous time signal. What are the Dirichlet conditions? Basically, it's the same sort of idea, and they are met essentially by all practical signals of engineering interest. What's the first Dirichlet conditions? It must be absolutely integrable, okay? So you can't have a signal that goes on forever, that would require an infinite amount of content forever. Well, there's no device that we have that actually can persist or keep a signal going on forever. The second Dirichlet condition is that X has to have a finite number of discontinuities over finite intervals. You pick whatever finite length interval you choose, that signal cannot have an infinite number of discontinuities in it. Again, because we have devices, switching devices that can sort of cause discontinuities, they can never switch so fast as to give us an infinite number of discontinuities over a finite length of time. This is an easy condition to meet with engineering practical signals. And the last condition is that it has a finite number of max and min over a finite interval. Same kind of easy guarantee that this is something met by practical engineering signals. These are very similar to what we had for Dirichlet conditions for Fourier series. If you remember those, it said that it had to be absolutely integrable over a period. So we just looked over a period, that it had a finite number of discontinuities over a period, or it had a finite number of min and max over a period. Here, you can think of our period going out to infinity. So we are looking over the entire timeline from minus infinity to infinity. All engineering signals of practical interest and importance are going to meet these Dirichlet conditions. If we meet the Dirichlet conditions, then the Fourier transform converges pointwise wherever the function is continuous, and it goes to the midpoint value. And by the mid value here, I mean the average of the left and right of when we approach the point from the left and the right of some discontinuity. So much like we had done an example sort of like this for the Fourier series case, we just did a periodic replication of this. I could look at a little triangle function like that. That particular little triangle function could have this, we could look at it as being some signal x of t, could have some spectrum x of omega. I'm not going to worry too much about what the form of that is just yet. We're just going to say it has some x of omega. We could also have a signal like this, where I just take one point and I make it double what it was. Otherwise, it's just like that first x of t. So I'm going to call this guy x2 of t. x1 of t and x2 of t are identical except at a single point. Fourier is going to end up giving you the same spectrum for both of those. And in both cases, if I was going to reconstruct the signal using the Fourier transform, what would I find? I would find that it would match pointwise everywhere that those signals were continuous, so it would go everywhere there, and it would go to the midpoint at a point of discontinuity. I'm going to get all of that here, I'm going to get all of that here, and all of that here, in a midpoint there. What about that one last little point of difference? If I approach from the right and if I approach from the left, those guys go to the same point, so it's going to be right there in the middle. The construction is going to be the same. Fourier would not know the difference between these two signals. It would not be able to distinguish or tell a difference. It would not give us a different spectrum between x1 of t and x2 of t. Does that matter to us as engineers? Not really, because you could never generate the signal x2 of t. There's no way that you could generate a signal that was going along and then instantaneously and only for that one instant, for no width whatsoever, it just jumped to another value and came back down. That's not a practical engineering signal. So in many respects, we don't really care that our Fourier series would not be able to detect, if you want to call it that point, or would not be able to reconstruct that particular point. So let's do a couple of quick examples before we finish out this lecture. I'd like to go ahead and show the Fourier transform in action. We're just going to pick a couple simple examples. So my first example I'm going to do here is I'm going to go ahead and look at the signal e to the minus ATUT. Okay, and I'm going to go ahead and let that be equal to x of t. This is very similar to the first signal that we took the Laplace transform of. So if you remember, if we had some a greater than 0, let's just go ahead and assume that for right now. This is a signal that looks like what? It is a causal decaying exponential, something like that. We had taken a look at this guy before. We had done the Laplace transform of that guy, and we got an x of s as being equal to what? It was a 1 over s, right? And we had something like minus a, something along those lines, I think. So if we took a look at where that was, it had a root at a. And if a, oops, no, that should have been a plus. So it has a root at minus a. So, and that a being positive, minus a is going to be off in the left half plane, something like that. So we'd have a root like that. And we know that there was a region of convergence, and I'm going to go ahead and draw that region of convergence green here. It's everything to the right of that root. We know it's right because it was a right-sided signal. So we've seen that kind of guy before. So that was for a greater than 0. We could have also taken a look at an a less than 0, right? It still would have been a causal exponential, except for now it would have grown exponentially. The only difference there now is that if I had a less than 0, a root at minus a minus a becomes plus, so it's going to be over here in the right half plane. We still have our region of convergence pointing off to the right of that guy. Something, whoops, I'm going to go ahead and point off to the right of that guy, something like that. In either case, the Laplace transform existed. We'd like to look at this same signal, right, but we'd like to do it Fourier style. So we'd like to find its Fourier transform. It's an aperiodic continuous signal. So it should have a spectral density, some spectrum, some x of omega. What is x of omega equal to? It's an integral, right? Minus infinity to infinity of my signal x of t, right? E to the minus j omega t dt. We're getting rid of all of the frequency, or all of the time dependence, and moving over to the frequency domain. And so if we go back and we take a look at our original, I think I got that right. There it is, x of omega equaling integral of the signal times e to the minus j omega t dt, something along those lines. Okay, so let's go ahead and carry that particular operation out. X of t in this particular case is going to be equal to an e to the minus at, and we were still multiplying by an e to the minus j omega t, and because it was causal, our limits of integration are only going to go 0 to infinity, something along those lines. And then I'm going to have my dt in there. These are two exponentials, so the base is the same, the exponents are different, so I can just add the exponents together. So this is an integral 0 to infinity, and I'm going to have an e to the minus, and I'm going to have a plus j omega t dt. We know how to integrate an exponential. That is going to be an e to the minus, and I'm going to have a plus j omega t over minus a plus j omega. And I'm going to do that on limits 0 to infinity. Okay, well, it turns out in this particular case, if a, right, if a was greater than 0, and if you remember a greater than 0 was that case of a decaying exponential, so that's to say that this thing looked like a decaying exponential. If a is greater than 0, then e to the minus a plus j omega t, when t goes out to infinity, will decay. It's going to go to 0. So that time we would get a 0 minus, and then we're going to go to the lower limit. E to the 0 times anything is just 1, so I'm going to get a minus 1 over minus a plus j omega. And if I clean that all up, I get 1 over a plus j omega. If a was not greater than 0, but it was less than 0. The Fourier transform does not exist. Does not exist. Why not? Because then your e to the minus a plus j omega t, when t goes out to infinity, would blow up to infinity. Okay, and we'll come back to that in just a minute. So x of omega, right, equals what? It is 1 over a plus j omega if, right, a is greater than 0, and it does not exist if a is less than 0. I'm going to worry just or mostly focus on the part where it does exist, okay? So let's compare this guy to what we had seen before for the Laplace solutions. We had x of s as being equal to 1 over s plus a. What does Fourier do? Fourier looks where sinusoids are. It says, I'm not going to decompose a signal in terms of generic complex exponentials. I'm going to decompose it in terms of sinusoids. And where do sinusoids live in the complex plane? They live along the omega axis. They live along the omega axis. Fourier transforms are really a Laplace transform restricted to the omega axis. That's one way of viewing it. So I'm going to look at this guy where sinusoids live. S equals j omega. In the case of a greater than 0, right, in the case that we had a decaying exponential, in that particular case, where Fourier lives on that omega axis is in, right, it is in the region of convergence for the signal, which means it's going to converge. That means you're going to get an answer. If you take a look at what happens when a was less than 0, that's a growing exponential, right? Now the omega axis is outside of where the region of convergence is for that signal. Because it's outside of, we know we are not going to get convergent behavior, and the transform cannot exist. So this has got a couple of points. The first is that as long as your signal has a region of convergence that includes the omega axis, right, we are probably going to be able to get our Fourier transform type stuff from Laplace transforms through a simple variable substitution, through the substitution of s equals j omega. Let's try that here. If you do that substitution in here, what do you get? You get x of j omega. Let's just call that x of omega, right? And what does it equal? It's 1 over j omega plus a. Look down here at what I had for the Fourier transform by definition. I had 1 over j omega plus a, or 1 plus a plus j omega, whichever order you do it, it's the same thing. So we get the same thing whether we did it by the Fourier transform analysis equation or if we did it through a substitution of the Laplace transform, as long as the region of convergence includes that omega axis, which is where sinusoids live, which is what Fourier is all about. Let's take sinusoids instead of exponentials that might have exponentially growing envelopes or exponentially decaying envelopes. There is a tight connection between the Fourier transform and Laplace transform. Now, the Laplace transform always has a transform for this signal, regardless of whether a is greater than 0 or whether it's less than 0. All that happens different there is that the region of convergence just keeps moving, right? It keeps moving according to wherever the root was. We do not always get a Fourier transform existing for these exponential, causal exponential signals. So in some respects, you might think that Fourier is not quite as strong. It's not quite as capable as the Laplace transform is, right? It can't handle everything Laplace can because it only lives where the omega axis is, and a Laplace transform can exist. It can have a region of convergence for some part that does not include that omega axis. Okay, so that was one example. We're going to do one more and then we'll be done with this particular lecture. In this next one, I'm going to do probably the easiest transform you can dream up. So this is example 2, and I'm going to pick a signal that is just a little bit kind of weird. This is our hammer function that we use to whack systems to try to figure out what their behavior is, right? So if you think about applications of this Dirac delta function, what did we do? We took a linear time invariant system, we hit them with a delta function, and out came h of t. And if I had that h of t, I knew that the zero state response for a system could always be gotten by x convolved with that impulse response h. So If I could measure the unit impulse response, I'm supposed to know enough about that system to figure out the output, right? The output YZSR in response to any input you could possibly dream. DC input, middle frequency input, highest frequency input, multi-frequency input, doesn't matter. Whatever input you put into it, I'm supposed to be able to figure it out through that unit impulse response. Here's what I think intuitively we should expect that. If me whacking a system with a delta function tells me everything I possibly need to know about that system's response to any input, the frequency content of that delta function had better include all possible frequencies. Let's see if that is confirmed in the Fourier transform of that delta function. The Fourier transform here, x of omega, is what? It's an integral minus infinity to infinity of my signal x of t, and then I'm going to have an e to the minus j omega t dt. I'm going to go ahead and plug in what is my x of t. That was just a delta function, so I'm going to put in here delta t, e to the minus j omega t dt. Well, this is about as an easy integral as you can expect, because we know through the sifting property, right? So we're going to go ahead and use the sifting property here, that an integral here, the delta function's non-zero only when its argument is 0. So at 0, that delta function's non-zero. At 0, e to the minus j omega t is just 1, right? So we know that this guy equals 1 at t equaling 0, and we know this one is not equal to 0 only at t equaling 0. So at that t equaling 0, we sift out the value 1, right? And then we're left with an integral of a delta function dt, and we know that that integral of a delta function is 1. So what do we get? We get a 1 out of all of this. So if I have a time domain signal x of t equaling delta t, right? And I do a Fourier transform on that, I get its spectrum x of omega being equal to 1. What does that look like? That is that as a function of frequency, there is constant content from DC all the way out to infinity. The delta function, right, has frequencies going from DC out to infinity, all present and all in equal proportion. It is the perfect kind of function spectrally to whack a system and understand its behavior in response to any frequency, right? Because it's got every frequency in equal proportion in its spectrum. Okay, so next time we're going to continue our discussion of the Fourier transform. We're going to talk about Fourier transform properties, and we're going to continue doing many more examples of carrying out the Fourier transform and also using those properties to help us carry out those transforms.